All right. So anyways, we're doing these with the kinematic equations. And picking out things like VI, VF, A, T, D, and one of those things will be the unknown. If you read it carefully, it should be pretty clear what the unknown is, and just, we always need, if you look at all those equations and every form of them we wrote out, there's always 4 variables in the equation. So that means we always need 3 givens to be able to solve any one. If I can't get out 3 givens, then I didn't read it closely enough, or I'm missing something somehow, okay? Sometimes some givens are given in words rather than numbers, especially when they're 0. Like when something says it comes to a stop, that's basically telling you final velocity is 0. If something says it starts from rest, that means initial velocity is 0. Sometimes it may not even say that, but it's implied through this scenario that's going on, so you just need to use a little common sense and understand the problem. Alright, so anyways, number 1, an airplane accelerates down a runway at 3.2 meters per second squared. So right there, if we freeze, if we know our units well, 3.2 has to be what kind of value, since it has meters per second squared as a unit. That's only a unit for what? Did we learn? Nope, careful. Meters per second could be a velocity, but meters per second squared has to be a what? It also gives it away right here. It accelerates at that, right? That's an acceleration. So use units to help you if you struggle with listing givens. If it's in meters per second squared, it's got to be an acceleration. Right? It can't be a velocity, because that's not a unit for velocity. So we can start first by listing A equals 3.2 meters per second squared for 32.8 seconds. Seconds is obviously a unit for what? Time, so that's got to be T. Always want to list all our givens. Until it finally lifts off the ground, determine the distance traveled. We want to know D, but we don't seem to have enough stuff yet, right? We need 3 givens. But think of the scenario now. When an airplane reaches a speed to take off from the ground, it must have started from rest, right? You know, airplanes aren't already in motion. It says it accelerates for that long. Here's where we have to imply it starts from rest. VI 0. All right. So now we got to go to our equations. All right. And we got to find, first of all, one of the 4 equations. The easiest thing to do is go to the top equation and scan them. And once you find the equation that has all 4 of these things we have in our givens, then we find the proper one, that rearranged one. The top one might be the proper one. Who knows? But we got to find the equation that has D, VI, T, and A only. If it has any more than that, we can't use it. We don't have enough information. So if we look carefully, equation 2 has all of those. And equation 2 is already solved for D, right? The top one. So we don't have to go down the column at all. So we just write down the equation. D equals V initial T plus 1/2 GT squared. Then we plug in the numbers. D equals 0 times T. 0 times anything is 0. So that part will kind of wipe away. That's 32.8. So I had to write small on here. Plus 1/2 times, oh, that should be an A there, I'm sorry. That's an A right there. I know that's a little ugly. 1/2 A, 3.2, times the T. Running out of room, but I'll squeeze it in there. That's 32.8 squared. Alright, so, I know it's kind of ugly there, but you get the point. So this piece is gone because 0 times anything is 0, right? So really it's just 1/2 times 3.2 we got to run. 1/2, or in other words 0.5 times 3.2 times 32.8, and we got to square that last number. And I get out, I'm running out of room, so I'll put it kind of above here. I'll just draw an arrow. I get out a D equal to 1,721.3. I'll round to 1 or 2 decimal places if it has a lot of decimals, okay? We don't want to keep every decimal. Meters. And that sounds like a reasonable answer. We'll always circle or box our answers too. Because 1,721 meters would be the equivalent of 1.721 kilometers. Airplane runways are pretty long, even for small planes, right? You would expect to get a fairly big answer here. And I use this as an example of why this stuff's important. And that's simply how, like, if an engineer wanted to figure out if these are true specs of a specific plane, and that's like a kind of plane that wants to be like able to take off from an airport that's designed, you better know how much runway you need, right? You're not going to just randomly design it because maybe you didn't design enough, or maybe you designed way too much than you need and you wasted a bunch of money, right? So little calculations like this using the kinematic equation is a big deal in engineering with stuff like that. Any questions on that one, guys? Eventually, it's not going to be this week. Sometime mid next week, there's going to be a little quiz, couple problem quiz, like maybe a 3-problem quiz, and one's really similar to this, okay? So if there's any questions, you're not sure of something, it'll be open note, meaning you'll be able to have this equation sheet, okay? You don't have to memorize equations or anything like that. As long as you're able to pick out givens, find the right equations, and pop in numbers, it's not too bad. All right, and number 2, a race car uniformly accelerates from 18.5 meters per second to 46.1 meters per second in 2.47 seconds. Determine the acceleration and the distance traveled. So we want to find two things, right? This and this. We can only find one at a time. Let's start with acceleration, okay? I'll move over here. Now look, the first couple of numbers given, they're in meters per second. So there's got to be what? What did we say that was a unit for? Not acceleration, because acceleration was meters per second squared. So what are those units for? Velocities. The first one's the initial one, and we get up to this one, so that's the final one. Make sense? So we list that. V initial is equal to 18.5 meters per second. V final equals 46.1 meters per second. In 2.47 seconds, so that's obvious the time, 2.47 seconds. The first thing we want to find out is what is A, so we need the right equation, and that has VI, VF, T, and A. If we go back to this sheet, the only equation that has just those four variables is equation 1, right? But equation 1, the top equation, isn't solved for A, it's solved for VF, isn't it? All we got to do, once we know the equation, go down the column and find the one solved for A. And that would lead me to A equals VF minus VI over T. Plug in those numbers, and that's going to be 46.1 minus 18.5 divided by 2.47. I'll just write the final part of the answer over here. So we run those numbers, do the subtraction up top first, 46.1 minus 18.5 divided by. Now here's where we got to be careful. There's an easy calculator mistake here that you can make. Even if you get this far, which you're almost done. If you do in your calculator with no parentheses, this minus this divided by that, it will do it incorrectly. Because your calculators are programmed to do strict orders of operations. It will actually just divide the first two and then subtract off the other part. If you have division in your calculator, here's the best bet to be safe. Even if it's unnecessary, it'll be okay. So if you have division with some stuff in the numerator and or denominator, different operations go on, put the entire numerator in parentheses in your calculator and hit divided by the entire denominator. If you do that, you won't make a mistake, I guarantee it, okay? So if I do that, plug in all the numbers right, I'll round a decimal point or two again, is fine. I get about 11.2, and this is acceleration, so what's the unit? Meters per second what? Squared. So that's the first part of my problem. And speaking of a race car, it doesn't have to be a race car. Your How Stuff Works I gave you, we didn't discuss it last week since we gave it, but I will right now, and if there's time left, I'll show you a short, like, couple-minute video on turbochargers. That's what your How Stuff Works is on. So we've all probably at least heard of turbochargers on cars, right? Like even common cars have them, not just race cars. But the point of them is to to provide a better jump or a better acceleration. And they do that, is what you read, if you remember a little bit about it. They basically force more air into the cylinder, and your fuel becomes more combustible the more air that's in there. And that essentially makes your car more powerful. Right? We'll watch a little video if we have time here about it, but that's the gist behind them. There was more in what you read, but how it happens could vary depending on the style. But turbochargers are really becoming even more and more popular to put on smaller engines to get the similar power output of like a bigger engine. Like one of the biggest things in vehicles right now is like government mandates to cut down on pollution of trying to not to have like big, huge engines if you don't have to. And one way with very efficient turbochargers that could happen. Like a lot of even full-size trucks now have darn near the same capabilities with a turbocharged four-cylinder engine as like a V8. They're approaching almost the same power, and they save on gas, therefore there's less pollution and stuff like that, and they just keep getting better and better. It's probably not that long away till like in another decade or two, you won't even have V8s anymore because turbocharged lower cylinder cars and hybrids could go into the mix with that as well. We'll start replacing it and having just as much power as those big like gas hog engines, pretty much. Anyways, that's a little extra, but that's what we just read about recently, so I thought I'd bring it up. Alright, so I'm just going to then beside it solve for the D. Alright, now I'm not going to relist the givens, just remember those are on my givens. I'm not going to use the A, I already solved for that, right? I'm going to use these same givens over here to find out how far it traveled during all this, alright? So I need the equation that has D and these three things, right? D, VI, VF, and T. That would be equation 4, and it's already solved for D. So we use it in its main form that's at the top of the column. D equals 1/2 VF plus VI times T. We just plug in the numbers and run them carefully. So that would be 46.1 plus 18.5 multiplied by 2.47. Write it on here. And I'm writing over the next one, but we skipped this one anyway. So running these numbers carefully, 46.1 plus 18.5. They're in parentheses, so I'll do those first. Times 1/2, or in other words, times 0.5, times also 2.47. We run them right, we get about 79.8 meters for this car to accelerate from this speed to this speed. That's the acceleration rate. So just so we understand what the acceleration rate means. Meters per second squared means every second that passes that this car is speeding up, it speeds up by 11.2 meters per second. So if it did it for 2.47 seconds, it goes from this speed to this speed. And this tells us how far it went to speed up that much. Right? So this is the kind of stuff, not these same numbers, but often when you see a commercial on TV for a sports car that's trying to boast how fast it is, it'll often tell you in the ad, like, this car could go from 0 to 60 in whatever amount of seconds. It's essentially telling you, describing an acceleration rate. They're not running the numbers through the formula, but they're basically, obviously, something that could go from 0 to 60 in 4 seconds is faster than something that could go from 0 to 60 in 8 seconds, right? Because it happens more quickly. So that's really what we mean by acceleration rates, thoughts like that. Any questions so far? All right, we skip number 3. Let's go down to number 4, a bullet. Bullet travels really fast, right? It leaves the rifle with a velocity of 521 meters per second. Meters per second, that's got to be a what again? Velocity, right? But is that VI or VF? It leaves it. VF. This is another one where we got to assume VI is what? 0, because before it starts, before we pull the trigger, it's not moving, right? So it doesn't tell us that, but the situation makes sense that it would be that, right? Start from rest and then pull the trigger, it gets up to 521 meters per second. what's the acceleration through the barrel? So we want to find A. If it moves a D of 0.84 meters, that would be the length of the barrel. All right, so VI, VF, A, and D. In other words, the one that doesn't have P is the equation we use. That would be equation 3, and we need to find it solved for A. So we got to go down the column for equation 3, and we should find this formula that we rearranged the other day. VF squared minus VI squared over 2D. So plug in our numbers. 521 squared minus 0 squared, which of course that's going to be 0, all over 2 times 0.84. Again, if you're going to plug in everything at once in your calculator, you should really put parentheses around the whole numerator and around the whole denominator so it doesn't make a calculator mistake. Another option, if you don't like doing that, is to figure out what the numerator is as a number all by itself. Calculate what this is as a number all by itself, then divide those two results. If you do that, you should get the correct answer as well with no mistakes. So anyways, 521 squared divided by 0.84. You do it right. This is a really big value. Still round at the decimal point. Actually, we'll round it to 2 decimal points since the first one's 0. And that's the acceleration, so it's meters per second squared. But wouldn't we expect a crazy big acceleration? A bullet is going from 0 to 521 meters per second in a barrel that's this long of a rifle. To get to that kind of speed, don't you have to have a crazy acceleration? Of course, we know bullets would have a crazy acceleration caused by the explosion of the powder in the bullet that forces it out so quickly. So that's a reasonable number, even though it's crazy huge. Over 161,000 meters per second squared. We'll get to forces more later, but it's not hard to accelerate very low mass things like a bullet this fast. But the higher the mass eventually we'll learn, then it's harder to accelerate. But doesn't that just make common sense? It's easier to throw a baseball really fast and accelerate it pretty fast as compared to if I had a bowling ball. Could I throw a bowling ball and accelerate it as fast? Absolutely not, because it's a lot heavier, right? It has more mass. So there's a force factor into this that will come in later. So right now we just need to know how to find the acceleration. All right, flipping on the back page. Number 5 we had to do. Another runway one. An engineer is designing a runway for an airport. Several planes will use the runway, and the engineer must design it so that it's long enough for the largest planes to become airborne before the runway ends. If the largest plane accelerates, there's a number of meters per second squared, it's got to be an acceleration, at that rate, 3.3 meters per second squared, has a takeoff speed, that would be VF, of 88 meters per second. Then what's the minimum allowed runway length? Well, again, we'd assume the plane started from what? 0, rest. So VI is 0. And the runway length, that would be a D, right? How far you need to make it. So we need to find D, A, VF, and VI. The one without T, that's equation 3 again. And we find the one solved for D. And it would be the one that looks like this. D equals VF squared minus VI squared over 2 times A. Plug in the numbers, that's going to be 88 squared minus 0 squared divided by 2 times 3.3. Again, if you want to plug that all at once in your calculator, you would parentheses the whole top and the whole bottom. And we would find that D equals, if we calculate it correctly, 1,173.3 meters. If we're good with that, then even the largest plane that needs to take off would be good. But again, something to consider. This equation gives me the exact distance the runway needs to be. If you're an engineer designing it, are you going to design it the exact minimum distance? No. Because what if something happened, right? You would then tack on some extra for a little safety. All right, at least you know the minimum where you have to be, and then you make it a little bit bigger than that, just so in case it would take a little bit longer for some reason to take off. All right, 6 we skipped. Going on to number 7. We did 7, right? I think so. Yeah, oh yeah, this is the one I just told you, don't worry about sketching anything. So ignore anything about sketching. So Renata Gas is driving through town at 25 meters per second and begins to accelerate at a rate of -1 meters per second squared. Eventually comes to a stop. So this time our VI, we're already moving, right? 25 meters per second. Our acceleration rate is -1 meters per second squared. And we come to a stop, so VF is 0. Use this, now ignore the graph thing. We use this information, not a graph, to determine the distance, so we need to know D. It looks like equation 3 is getting hit hard a lot here. We're going to use that one again to find D. So one more time, VF squared equals VI squared over 2 times A to find the D. Plug in the numbers, and that's going to be 0 squared minus 25 squared, all divided by 2 times -1. Run those numbers, and our D will, down here. I don't want to write over that one, so I think I did that one. Hold on. So I'm going to put it up here, since I got room up here, okay? Okay. Be careful on one thing with this. Look at this calculation right here. This minus, does it get squared? No, only the 25 does. That minus was there from the formula, right? And this number down here is a -1. A negative divided by a negative should come what? Positive. As long as you plugged it in right and remembered that negative, that should be fine. But just so you look ahead to make sure it does, it should come out positive. So 25 squared divided by 2. You should get out around 312.5 meters. Another just real-world example of this. When you slam on the brakes, not saying this person did, but let's do a conceptual variation of this. If you slam on the brakes and you're, even with anti-lock brakes, if you're going pretty fast and slam them on, they could still lock up. And if you're going pretty fast and slam them on, you're going to leave skid marks. And in those situations, crash scene investigators are trained to use physics formulas like this by measuring skid marks. Let's say there's an accident, but nobody saw it. All right, there was no witnesses other than like the person driving, who may or may not be lying, right, about what happened. So if there's skid marks present, using the length of the skid marks could show the stopping distance. Does that make sense? And if you know the stopping distance and the fact that the car, where it stopped, you could extract some data. Also using some frictional values we haven't talked about yet between rubber and asphalt. They could estimate within a pretty reasonable amount of air how fast that car was going when it slammed on the brakes. And that can actually hold up in court as evidence, if the evidence there to be able to measure that. And there's other things similar to that they could do. But it all comes down to physics and being able to use physics equations and knowing what to measure and figure it out. Alright, so... No, 8 I didn't say, right? Yeah, 8 I didn't, but 9 we did, right? No, 8 and 9, never mind. Because those had a little extra something. So I think 7 was the last one, right? Alright, any questions on any of those? Alright, if you fixed any you got wrong, take a second to upload that so you get a couple points around it complete. And you'll be allowed to have anything out. Probably more than likely next Wednesday will be a little quiz on this, okay? Like maybe 2 or 3 problems. Just make sure you show the work like we did here. We'll have everything open to you. So go ahead and turn that in.